Welcome to ECE 6340 at the University of Utah. Today we're going to begin the finite element method. This method is very popular for solving for electromagnetic fields, particularly those in regions that have curved surfaces. The reason that it's so popular is because if you have a curved surface, you can model this surface very well with triangles, as I'm showing here, or perhaps with quadrilaterals. These are the typical types of element shapes that we have in a finite element grid. These model the curved surface much better than those that we have learned previously that have been standard rectangular elements that you can see don't model surfaces as curved surfaces as well. So to begin, let's consider the potential, the voltage, in a two-dimensional plane. If we had several elements, let's suppose we had a few triangles here, for example, we could model the potential across this whole system as being the sum over all of the elements, 1 to n, in this case we have 3 elements, of the potentials on each one of these elements. The potential is assumed to be linear within the element and to be 0 outside of the element. Another way we can write this is 1 to n of v of x and y times some kind of basis function over each of the elements. Now let's consider one triangular element and consider what the elemental voltage is. If this is node 1, 2, and 3 on that element, I can have potentials at each one of those nodes, VE1, VE2, and VE3. This is the location x1, y1, x2, y2, and x3, y3. So VE at x and y is going to be modeled as being linear between these 3 points. So we're going to have a plus bx plus cy. If instead we had some kind of quadrilateral element, 1, 2, 3, and 4, then we would have an elemental voltage which is also linear, and it would take this form, a plus bx plus cy plus d times x times y. And both of these would be 0 outside the element. Then we could write the electric field on this element, or the elemental electric field, which would be the negative gradient of the potential, and that would be negative the derivative in the x direction and the derivative in the y direction, all operating on VE of x and y. For the triangle, this would give me minus b in the x direction plus c in the y direction. So we can see that if the potential is linear, if the potential varies linearly within the element, then the electric field is going to be constant within that element. Then we use these equations to define something that we call the governing equations, or the stiffness matrix. Now the governing equations are considering each of the potentials in the corners, so the nodal potentials VE1, VE2, and VE3. Let's write a matrix equation for what those would be based on our triangular element, a plus bx plus cy. So if we wanted to write a matrix equation for them, it's going to look something like this. All right, well, let's see what VE1 is. VE1 is VE at x1, y1, so that is a plus bx1 plus cy1. Let's just write that equation up here. That's going to be a times 1 plus b times x1 plus c times y1. If we wrote for VE2, that would give us VE at x2, y2, which would be a plus b x2 plus cy2, so it would be like this. And similar for the nodal potential 3. Now the things that we have here is, this is what we would like to be able to find. This is defined. So this we can say is known. It is based on the size, shape, and location of each element, and these values are unknown. So if we solve for A, B, and C, that is going to be the inverse of our matrix times VE1, VE2, and VE3. So just bring this matrix right down here and take its inverse.